Hi there. So if someone's there, it's quite helpful for you to write just a message in the chat so I know the audio is working properly. All right, there's a few people here. If you can hear me, and you can chat, then it's quite helpful if you just write a message so I know that the audio is working and the video is working. Otherwise, it's hard for me to know. Okay, Peter, thanks. Okay, very good. Okay, so welcome back, everyone. This is going to be hopefully the lecture where we can finish our analysis of the Airy equation, and then finally I'm going to give you some of the big picture ideas behind using these techniques in exponential asymptotics before we go on to more complicated problems. It's taken us a little while to get through this problem, but it's good to go through some of the details, I feel, even though it's a little bit painful, because if I give it to you in too general of a way, it can be hard to actually know what to do in practice. But let me try to recap where we are. So this is our standard Airy equation. Epsilon squared y double prime is equal to x times y. And then we did this transformation so that we could expand A into a proper series. Okay, so we just substituted this ansatz into the differential equation to develop one for A. And in doing so, we had the equation of s prime squared is equal to x to the 1/2. You integrate this once, so that gives you that s is equal to plus or minus 2/3 x to the 3/2. And that became the exponential. So we ended up attaching ourselves to the exponential decay, the minus 2/3 x to the 3/2, because we're anticipating a solution which decays on the right and then oscillates on the left. Okay, but you should keep in mind the other branch of that square root function, because we're gonna bring it up again in a minute. Okay, so now having made this choice for s, that becomes our differential equation for A, and at this point you can forget where you started off from and just think of the analysis of this differential equation. You then substitute in your regular perturbative expansion in A here, in powers of epsilon, and you're looking to characterize these late terms for reasons that will hopefully become quite clear, but the importance is to figure out how the terms of this asymptotic expansion are diverging. And substitution of this into the equation and then looking at the limit as n goes to infinity had given us that chi of z was minus 4/3 x to the 3/2. And it also gave us that q of z was a constant that we had to figure out over a power over x to the 1/4. Okay, and then the question, well, how do you figure out what the gamma is and how do you figure out what the lambda is? The gamma we found to be 0. And to figure out the gamma, you just have to take this expression here as z goes to 0. That's where all the action is. And if you just put in n is equal to 0 here, in order for you to get a match with A0, a naught was 1 over x to the 1/4, it turns out that this gamma has to be 0. Okay, fine. To get this lambda was much more problematic, and I had begun to walk you through some of the ideas of how to determine this lambda. Sorry, I said lambda. In order to figure out this constant lambda, I'm not going to dwell too much on the details and just kind of give you the broad overview. So to find lambda, what you're going to do is you're going to rescale your problem near the singularity at x equal to 0 or z is equal to 0. So you're going to set a of x to be g of, a of z to be g of another variable which we call zeta over x to the 1/4. And again, this x to the 1/4 is just a convenient scaling because basically I know that a naught, the first number here will be 1 over x to the 1/4. So it turns out to be convenient for me to set this x to the 1/4 scaling so that sort of the leading order of g is then 1 in order for it to match with this term here. The other thing that I want to do is I want to just set this, make a coordinate transformation. And the appropriate coordinate transformation was to set this singulant, minus 4/3 x to the 3/2, to be epsilon times zeta. And in the last lecture, I gave you the intuition of why that is the case, that if I set this to be epsilon times zeta, then this term, which is epsilon to the n times an, the epsilon disappears. And basically, the inner region is characterized by all the terms of your asymptotic expansion becoming the same order. So that sets the scaling of your inner region. Okay? So then you basically stick this into the differential equation. You have to do a bunch of conversions from ddx to dd zetas. And you're going to get a differential equation without any epsilons now in the inner region. And after that, what you can do is then expand g of zeta into a series expansion in powers of zeta. So the goal is now basically to figure out how this expression here, which applies in the inner region, so this is the picture in your head. Here's the complex z-plane. Here's the so-called turning point, or the singularity, at z is equal to 0. Outside of this little bubble, you have an expression that looks something like this. Okay, so there's your factorial over power, and then this is like x to the 1/4 times the chi to the n. Gamma is just 0. This is a lambda here. And basically, as this expression is taken towards 0, all these terms become disordered, and they become the same order as each other. A1 becomes the same order as A0. Epsilon A1 becomes the same order as A0, etc. And the size of this bubble is basically order epsilon. Turns out to be order epsilon. Order epsilon to the 2/3. Okay, so you zoom in to an area order epsilon to 2/3, and then you develop the inner equation here for g of zeta. And then you attempt to expand this expression out in the limit that zeta tends to infinity. And that will allow you to match things between the two series, and that will allow you to determine the lambda here, which will be related to the expression for gn as n goes to infinity. Now, the problem is that in a general, for a general problem, this gn as n goes to infinity, you can't really write down in closed form. In other words, this lambda, there's no closed form expression for that. for the Airy equation, it turns out you can, because the expression for Gn is sufficiently simple. The recurrence relation for Gn is sufficiently simple. It's some kind of ratio gamma functions. But this is only because the problem is so simple, because it's a linear problem. For other problems that are not as simple, it won't be this case. So for other problems, so what you'll get is a recurrence relation that will tell you how to generate the coefficients Gn, and it'll be some recurrence relation which will give you Gn plus 1 as a function of Gn. And you can numerically solve for this recurrence relation. So this is n and this is Gn. And what you'll notice when you do this numerical solution is that, firstly, Gn diverges, as you would expect it to, because the outer solution also diverges. But if you plot Gn over your anticipated scaling for the outer solution, so you're anticipating that these numbers will diverge like a factorial, like gamma of n, then the kind of graph that you'd see is basically something like this. And it would give you a discrete set of points. So you might solve this to n is equal to 500, and it would give you a discrete set of points, and the value here is some constant. So how do you relate this constant to the constant that you're looking for, this lambda? Well, you can just think of the expression. So I have epsilon to the n times an in the outer region. This is basically like epsilon to the n times lambda over x to the 1/4 times the gamma function over zeta, epsilon times zeta to the n. That's why you see the scaling here had worked, because the epsilon to the n will cancel with this epsilon to the n here. And from the inner region, if I think of the nth term of the inner region, this will be Gn over zeta to the n. I had scaled my inner region by an x to the 1/4. I told you that would be useful scaling. And this will approach some constant over the factorial function x to the 1/4 times zeta to the n. And so you see the constant, we've set things up so that the constant will be exactly lambda. So even if you couldn't do the problem analytically, you can just put the equation for Gn, put this recurrence relation into a computer program, see if you can extrapolate out what the constant has to be, and that would give you the constant. But in this case, you can solve it in closed form, and actually the constant is 1 over 2 pi. Okay? But this procedure of kind of zooming in near the inner region and then matching with the outer region has given you a scheme to figure out what this prefactor is going to be. For most general problems in these kinds of exponential asymptotics, finding this constant is really the most painful part. And it turns out that for most problems, it requires a huge amount of work to find this constant. It is often not as easy as it is here. This series can be, this recurrence relation can be converging really slowly, for example, and you have to do some extra work to speed up the convergence to figure out whether it does approach a constant. And a lot of times what you're interested in is the fact that the constant can't be 0. But if it's some number, it's not so important, at least experimentally, what this number is. The other components of this analysis, including the chi, the gamma, those are often more crucial. So though this is the most painful part, determining this lambda in the procedure is actually probably not that important of a part. As long as you know there is a number lambda that's going to work. Okay, so at the end of the day, what we've done is we've given you the tools you need for the Airy equation to figure out all the components of these late orders. And the philosophy that we have is that once you know these late orders, you're kind of done. Because what you'll do is you're going to optimally truncate, and you're going to smooth the Stokes line. And so you're going to write A into a series which is truncated from 0 to capital N, or minus 1, plus the remainder. You're going to stick this into the differential equation, and then you're going to get a linear equation for the remainder, which on the right-hand side is going to be forced by some epsilon to the n expression. Right? And we've done this for other problems as well. It's always going to turn out to be the case. Now, the equation for the remainder, you're going to attempt to write down the solution. And the solution form that you're going to take is a Stokes multiplier, an unknown function to be determined, s of z, say, and you're going to pick the exact components that were associated with the divergence. At the end of the lecture yesterday, someone had asked this question of, is it always the case, essentially, that these components will be the same as these components? And the basic answer to that is yes. It's essentially that case, because if you go through and think about what happens when you take derivatives of this expression, when you take a derivative of Rn, you're going to have a 1 over epsilon term from this factor times chi prime. And when you take a derivative here, you're going to have an n plus gamma come up. This will produce a gamma function of n plus gamma plus 1 times a chi prime. And there's essentially an analog between every operation you do here in epsilon and every operation you do here in n. And it turns out that the operations are essentially the same. And so that's why there's this link between the divergent terms and the remainder. And I'm going to show you a different way of seeing that link in the lecture later today. Okay? But that's why I've kind of hinted at this idea of decoding the divergence, and that's what we mean. We try to obtain the divergence and then use them in the expression for the remainder. We can follow the same procedure. We can substitute this expression of the remainder into this equation for the remainder. We can put in our divergent ansatz into the right-hand side here. We can then attempt to optimally truncate, choose the value of n, and then expand by Stirling's formula. But you're going to end up with the same thing, which is that you're going to end up with the conclusion that there's a jump in the multiplier of s of z, and this jump is basically 2 pi I over epsilon to the gamma to leading order in epsilon. So this procedure involves a great deal of algebra. We've done it for the exponential integral and the complementary error function, but it's actually going to give you the same answer, which is that the remainder is always going to switch on 2 pi I over epsilon to the gamma times QE to the minus chi over epsilon. And so that's why we say that as soon as you can get this form, if you can figure out what the divergence has to be, you can almost jump right to the final conclusion, which is this is going to be the switching. Okay? So what is it for the Airy equation? Well, for the Airy equation, it would be 2 pi I over epsilon to the 0 because gamma is 0. Q is 1 over 2 pi. That was the number in front that I said required a little bit of work to get. And then there was a 1 over x to the 1/4. And then it's e to the minus 4 over 3 x to the 3/2 over epsilon. Okay, and you can see 2i cancels with 2i, and I essentially have I over x to the 1/4 e to the minus 4/3 x to the 3/2 over epsilon. Bit of a mouthful. Okay, right. So let me now give you the summary, because this is, remember, this is a remainder in A. It's not the remainder in in Y, in the original differential equation. I want to go back to that remainder in the differential equation. And also, the other thing is I've not told you about the Stokes lines for this problem. So this switching is happening across these quite spectacular Stokes lines. So what's the formula that we have for the Stokes line? So let's figure that out. Okay, so the formula for the Stokes lines is actually, again, almost a universality. Just like the way that the exponential was switched on followed this formula, the Stokes lines are given by, it's given by where the imaginary part of chi is 0 and the real part of chi is greater than or equal to 0. And there's actually no easy way to see this. Okay, you can see it when you do the Stokes smoothing, as we've done it in the past. There's no easy way to see this right now, but I'm going to show you a shortcut to see this in a minute. But what does this look like for this problem? Well, we want the real part of minus 4/3 x to the 3/2 to be greater than or equal to 0. So if I let, I keep on going to x's. These should be z's. I've converted to using z's. So if I let z to be r e to the I theta, this tells me that I need 3 theta over 2 plus pi is equal to 2n pi. It has to be multiples of 2n pi for my real part to be to be positive. Right? So this tells me that theta is 2/3 times 2n minus 1 times pi, where n is integer. Okay. Now, the first one where this occurs is if I set n is equal to 1, I have 2 pi over 3. So here's the real z-plane. Here's the imaginary z-plane. And the first switching happens at 2 pi by 3. An angle of 2 pi by 3 from the positive real axis. There is no secondary switching. If I take n is equal to 2, I have 3 pi over 3 times 2, so I end up with 2 pi. So the secondary switching happens here. But for reasons which will be clear, let's not think about this one. The reason why, and I can also put in n is equal to 0 as well, and that will give you minus 2 pi over 3, but I don't want to think about that for the moment. And the reason why is because I want to take my branch cut. So because I have a 1/2 function here, I have to cut the plane, otherwise I'm going to have multi-valued functions. And I'm going to think of taking the cut here in the positive axis. So I want to think about starting with a solution in the upper half plane, going around, and then getting back to the negative real axis here. The solution is exponentially decaying for this positive bit here, and then it's oscillatory on the negative bit. And as we know now, so out here, I have a solution which is essentially 1 over x to the 1/4. Keep on writing x. I think I might have continuously written x in the last couple minutes, but if you see an x, chances are it's supposed to be a z. I think I converted to z's for the differential equation for a. And then it's e to the minus 2 over 3 z to the 3/2 over epsilon. X was the original scaling for the Airy equation. Z is the version where we introduce the epsilons. Okay, so all the x's, I think, for the last couple of minutes should be z's. Okay, and then now we know that when, and then there's additional terms, right? And then now we know that when you swing this across the 2 pi over 3 line, you're going to switch on a term. And so on the left-hand side here, it's essentially the term that you had, 1 over z to the 1/4 e to the minus 2 over 3 z to the 3/2. Let me write it in a different way. I'm sorry. Let me write let me write this in a more careful way so that you can see the structure of the a's. Okay. So in the region out here, the leading term that you have is essentially a naught of z, and in that case it's 1 over z to the 1/4. And then you have the order epsilon term and the order epsilon square term, etc. You'll notice I had an exponential out here, but I'll introduce that again in a second. As I swing across this line, I then have the original z to the 1/4 plus all the corrections, but I'm going to have that switching. And the switching I found was essentially I over z to the 1/4 times e to the minus 4/3, to positive 4/3 z to the 3/2 over epsilon. I'm going to erase the 2 pi over 3 line here. It's too confusing, too much stuff. So as I cross that 2 pi over 3 line, this guy switches on. Okay. And in the original coordinate system, you have to remember the original coordinate system, you prepend a minus 2/3 z to the 3/2 essentially over epsilon. You basically prepend that on. So that's your exponential decay on the right. But on the left, when you multiply that by e to the minus 2 over 3 z to the 3/2, this becomes a positive e to the 2/3 z to the 3/2, which is the other pair of the exponential. Okay. Okay, so the missing element here is basically the fact that when you switch on this term here, there's another analysis you have to do with the asymptotic expansion that corresponds to the term that you switched on. And that would tell you that when this term here crosses the line 2 pi over 3, or the line 4 pi over 3, it switches off the original base expansion. Okay? And to do that analysis, really all you want to remember is that you remember when we did the rescaling, when we wrote y into a, e to the s of z over epsilon, and we found the formula for s, it had two branches. S was basically minus 2/3 z to the 3/2, or it also had the plus branch, and we took the minus branch because that was the one that we wanted to localize around. But if you switch on this term here, there's an analogous study you have to do with the other branch, but you would just end up predicting kind of the mirror images of each other. And when you do the Stokes line for that one, you would find there's another Stokes line down here, and you would switch on the other exponential. Okay? So this is essentially how you do the analysis of the Airy equation exclusively without any integral transformations. You see, you have predicted the divergence, you've used the divergence within your equation for the remainder, you obtain these terms which are switched on, and in doing so, you'll also find out where the Stokes lines are. The Stokes lines are where the real part of chi is greater than or equal to 0. This turns out to be universal. This technique of finding factorial overpowered divergence using the singulant function. The singulant function is the chi to find the Stokes lines. The formula is always the real part of chi greater than or equal to 0. And the switching is almost always this 2 pi I over epsilon to the gamma formula that we found before. All right? So for the last part of the lecture, I want to explain to you how you can see this universality in the switching. There's a trick to it, okay? And so I'll show you the trick. And the trick is done using something called Borel summation. Because otherwise it's not very easy at all to see, why is it the real part of chi greater than or equal to 0? Okay, and there's actually a more rigorous way of doing this demonstration, but I'm not going to do it in the rigorous way. I'm just going to be doing it in a way where I'm going to be manipulating integrals and sums in ways that might make you feel uncomfortable. But the rigorous way is actually largely the same procedure. Okay, so let's take our asymptotic expansion, and for simplicity, I'm just going to write it in terms of y, and think of if an asymptotic expansion for y in that form. Okay, and so we know that in general this thing will diverge for singular problems, and this yn will diverge like a factorial over power. And so we might split that into our into an expression that involves the remainder okay, this Rn of z. And I'm going to make the assumption that I can estimate the remainder with a factorial over expression. So I'm going to estimate this remainder. So this is essentially an infinite sum from capital N to infinity, and I'm just going to stick in my factorial over power there. So this is essentially epsilon to the n times, I'm going to assume that it's being predicted by a factorial over power expression. Okay. So this part is obviously not true because this is only one, this is kind of the dominant part of the remainder. There are other parts that there might be more than, it's more than this, but we're just going to make the assumption that the remainder, which involves the infinite sum over the rest of the terms that you've not included in your truncation, is approximated in that way. Okay. Well, what I can do is I can rewrite the gamma function as an integral and then just figure out what that might tell me. So I can write q of z here, and then my sum from capital N to infinity, okay, I'm going to have an epsilon to the n, and then I can write down an integral expression for the gamma function. So this is an integral from 0 to infinity of e to the minus t, and then this is t to the n plus gamma minus 1 dt. Okay, and then I've got my chi included as well. Okay, so that's all fine and good as long as your gamma function stays away from the singularities. But the contentious step that we're going to do now is we're going to swap the integration and the sum. That's the contentious step. So, but we're just going to assume it to be true. I can write a question mark if I like here. And I'm just going to swap the summation with the integration. So I have q of z here. And then I have an integral from 0 to infinity of e to the minus t over t. And then I'm just going to rewrite it so that I can use a geometric series for the sum. So this goes from capital N to infinity. I'm going to put the t together with the chi together with the epsilon. So I'm going to have an epsilon t over chi to the n plus gamma, like so. Suppose I'm missing a dt. And then because I put this to be epsilon to n plus gamma, I'm going to have to divide out by an epsilon to the gamma here. Okay? And again, without thinking about it too hard, we're just going to use the formula for a geometric series and assume that we're just going to use the formula for the geometric series. Let's write that back out here. So then our remainder is q of z over epsilon to the gamma is going to be an integral from 0 to infinity. And then I have e to the minus t over t. And then I use the geometric sum, but because I'm not starting from 0, I'll have a little term to a factor of epsilon t over chi down here with an n plus gamma over 1 minus epsilon t over chi dt. All right. Okay, so now the next thing I'm going to do is I'm just going to rescale things so I can look at things in a more familiar way. I'm going to set epsilon t to be equal to a new variable w, and then just do a coordinate transformation for that. Okay, and so that gives me q of z over epsilon to the gamma, an integral from 0 to infinity, and then I have w over chi to the n plus gamma over 1 minus w over chi. I think I have a 1 over w factor as well here, times e to the minus w over epsilon dw. Okay? Right. So now we get to use some simple integration and figure out what's going on. So the integration now proceeds in the w plane. Okay? And I'm just going to erase, I'll erase this one here as well because I won't need the t expression anymore. So here's our remainder. I guess this is twiddles. Okay? And remember that z is something that we're given. So we just evaluate this expression for different values of z. And now we have to do the integration in the w plane, and the integration in the w plane just goes from 0 to infinity. So if I draw a picture up here, in the z plane, the left picture will be the z plane, say. The right picture will be the w plane. And in the w plane, you just have to integrate from 0 to infinity like that for every value of z. So z might be over here, say. You might evaluate that value as z. Now, you have to be careful, and you have to be careful at basically w is equal to chi. And there might be a singularity here at w is equal to chi, because your integrand is singular at that point. Okay? But actually, this integral is just exponentially decaying along this axis. And so you can essentially just do integration by parts on this integral in the same way that we've done so. And what you'll find if you do it this way is that you can almost see it that if I just take w equal to 0 on the denominator here, I'll just have, on the top, I'll have w plus gamma minus 1, right, over a factor of chi. Then this is e to the minus w over epsilon. Now you have to integrate this from 0 to infinity, and you're simply going to rediscover the gamma function when you put this in. And it's simply going to tell you that the next term that you didn't include in the remainder is just the gamma function of n plus gamma, which is what we started off with. So that's not too useful. But you can see that the basic integration along here is in essence going to rederive the asymptotic expansion. That's not surprising. But then what happens though is that as your z point moves around in the left plane, this chi of z function is moving around in the right plane. And at some point, it may be that when I move z around in the left plane, okay, I may cross some line. At which point this singularity has hit the axis. And at that point, I can no longer integrate in a straightforward way around it. Okay. I think for illustration, I'm going to assume that it crosses going the other way. So that it's crossing, so originally my w equal to chi point is here. And then it's going to cross and then go up into the upper half plane. Okay? So in the first situation, where there's no crossing, right, I have this scenario where I just integrate directly from 0 to infinity. I don't have to do anything special involving the point w, and I'm just going to rederive the basic asymptotic expansion. In the second situation, I have crossed from here across some critical curve, and that critical curve, during that operation, I've hit the axis, and then I'm above the axis. But in order for me to do that, when I perform this integration, I have to do it in the following way. I have to go around the pole. Because if I go around the pole in this fashion, if this point were to descend back to its original value, I would recover my original integral. So you see that after this critical moment has happened, you now need to include a residue contribution. Where is this critical moment? Well, that critical moment is when this singularity has crossed the real axis, and hence the real part of chi is positive, and the imaginary part of chi is 0. And that's where that condition comes from. Well, I mean, there's one way of seeing where that condition comes from. Right? What is that residue? Let's figure that out. Well, the residue will be q of z over epsilon to the gamma times 2 pi I. If I cross it in that way, where I'm rotating clockwise, it'll be a minus 2 pi I. And you can figure it out. You have to just rewrite this in a more convenient. You want to often write it in that way. Then you'll have a factor of chi out there. But you can double check that the residue contribution, when that happens, is exactly the form that we initially predicted. I think there's another negative that cancels out this positive. Whether there's a positive or a negative, it depends on whether you're crossing the Stokes line in one way or the other way, and whether or not this singularity is coming up or it's coming down. So best not to think about it right now, because we'll get ourselves into knots. But it's going to be basically something like this, modulo a plus or minus sign, depending on the way that you're approaching. But that's where you see this universality come into play. You also saw that this universality comes up if you just make the assumption of a factorial over power. That as soon as you have that factorial over power expression and you play with the integrals in this way, this has to pop out. And you also see the universality of the Stokes line, why the Stokes line condition is that. This is the simplest explanation I know where you can see this a little bit more concretely for a general problem, you see that this condition emerges when this singularity crosses the axis. Now this picture here is sometimes called the Borel plane. Depending on the context, some people might mean something a little bit different. But actually, there's a way to, so here we've presented it in a bit of an ad hoc way. We've manipulated integrals and summations, flipping their order of integration and summation. And we've also made some assumptions about the way that the series needs to diverge. And we've estimated the remainder just by replacing everything on the right-hand side with this factor over power. But there's a way for you to develop this argument a little bit more systematically, and we won't have to, but we're not going to deal with that. We're just going to accept that this is a universality. We're going to accept that there's different ways of demonstrating this, whether in this slightly ad hoc way or through each individual problem. You could do Stokes line smoothing, and you can do optimal truncation and develop it for each differential equation. I want to just point out another interesting consequence of this discussion, which is that you'll see that in this discussion, nowhere did I actually give any differential equation. I didn't give you any mechanism of how the asymptotic formula was developed. And so this is quite curious because it tells you that as long as you have a divergent series and it diverges in this fashion, you're always going to have an exponential, and it's always going to be of this form. You don't need a differential equation. You don't need an integral equation. There's this universality of any divergent series which diverges in this way is going to involve these exponentials. Okay, so let's recap some of the universalities of exponential asymptotics. And we're going to do it in a fairly general way, just to give you the idea of how you can do this for more complicated problems. And then finally, next week, we can start the more complicated problems. We're actually going to go back to the crystal growth problem. That was the very first problem that we presented, this kind of conundrum of why solutions don't exist to the crystal growth problem. And then from then on, we'll do more complicated things like, I suppose, water waves or Healy-Shaw viscous fingering, that kind of stuff. But what is the kind of general philosophy of how to do exponential asymptotics? Well, you can think of it as you have some linear or nonlinear operator n. And this can be a differential equation, it can be an integral differential equation, it can be an integral equation, it can be a PDE, but you have something that depends on an independent variable x and then a dependent a solution y of x, and then its derivatives, etc., and then a small epsilon. Okay, and again, I struggle a little bit because I'm trying to encapsulate a huge range of problems, right, in many different areas of science. But for the moment, let's just think of it as I have a problem. It involves some small parameters. It involves ODEs or PDEs for an unknown y. Etc. And it can be nonlinear. So it can be much more complicated than any of the things we dealt with. Okay? And okay, I might have some forcing function on the right-hand side with other parameters, etc. And you go and you develop your series expansion. So the normal thing is to go and let's just expand everything into an asymptotic expansion. And as we said, there might be some massaging you need to do to get it into this form. So for the Airy equation, it wasn't just a base expansion like this in algebraic powers of epsilon, but it might have been prepended by an exponential itself. Okay? And you find that this problem is divergent. And we explained to you that this is almost a generic property of any singularly perturbed problem, because it will be the case. So let me just write down some of my universalities. So the first universality is that usually the early terms, by an early term I mean y0, y1, etc. Have singularities in the complex plane. Okay, so for instance, we had the example where y0 was 1 over x to the 1/4. So this is actually a singularity right at the origin, but it can be something like 1 over x squared plus 1, so that it's completely smooth along the real line, but then it's got singularities at plus or minus I. It can be a tanh function. So again, something that is completely smooth, which is C infinity along the real line, but actually has singularities up and down the imaginary axis. It can be a set function, etc. But it's almost always the case for a very large class of problems that the early terms, y0, y1, etc., will have singularities in the complex plane. The second property is that unless a singularity is present in the early terms, sorry, let me rephrase that. Usually, the only relevant singularities in the plane that you have to be worried about, in the complex plane that you have to be worried about, are singularities in the early terms. And the reason why is because if you develop the next term of yn, remember how it always develops, you essentially always end up with a linear equation for the next term, yn plus 1, say. And this linear equation only depends on the previous terms of the series. So y1 will be a little linear equation for y1 dependent on y0, y2. Same thing will be something that depends on y0 and y1. And because it's a linear procedure at every order, unless you have a singularity in the complex plane which has been introduced by one of the first orders, it's not going to be present in any of the late orders. So usually higher order terms do not introduce singularities. But there are exceptions to this. Okay. Now, what's the next universality? Well, remember the procedure of which you're going to solve this differential equation. At every order, you typically have to differentiate previous orders. And if previous orders have singularities somewhere in the complex plane, you'll always increase the power of those singularities, and hence this leads to divergence. So divergence, I'm going to stop saying the word usually, and almost all of these are usuallys. There are exceptions to this, but they're usuallys. So divergence is the form of a factorial over power. So your yn will typically go in the form that we've been playing with, which is this expression, which is a factorial over power. So you just need to figure out what this expression has to be. And it turns out that for nonlinear problems, right, for complicated differential equations, it could be that because the divergence is such a strong behavior, it tends to, really separate terms of different orders. It could be that you would struggle to even find the first term of the series, but you can still manage to find the general form of the divergence. So a lot of people, when they see this kind of pathway to doing exponential asymptotics, they think, oh, surely I can't figure out what this thing is because I can't even figure out what my first, second, and third terms are. But actually, because this is a really it's a really powerful form of divergence. I mean, because you're making these extra assumptions about how the series is blowing up, you actually stand a chance of figuring out these components, the q and the chi. Okay, the fourth point is that Stokes lines are where this chi is real and positive. Okay? There's a different formula for the Stokes lines that I should present to you in another lecture if the base series is not algebraic like this in powers of epsilon, but if it has an e associated to it, like we had for the Airy equation, there's a slightly different formula you have to use, but I'm just going to present to you for this case here, for the case that your base series is going up in powers of epsilon. So as soon as you can figure out what the divergence is, you know where the Stokes lines are. And so for any physical problem you would have, usually a physical problem is real. You know, usually you're interested in real space. And so you develop the solution along the real line, and then you ask yourself, where are the singularities in the problem that generate the divergence? Then you go and figure out where the Stokes lines are. Say something like that. And then what you can do is you can figure out what are the switchings that have to occur across each of these Stokes lines. And as we pointed out, the switching is almost universal. That the exponential that you switch on is going to be something like 2 pi I over epsilon to the gamma times the form of your divergence. And that's why as soon as you get this, you can almost jump to here. Now this is the interesting question, which is where are those Stokes lines? Right? Do you always have to do exponential asymptotics for all problems? No, because these Stokes lines for a lot of physical problems may not actually hit real space. And so there are these exponentials floating around in complex space, but they never make it down to real space, or they're never of appreciable magnitude to be important in real space. But the interesting class of problems are those in which you go along in real space and then you switch on an exponential. And this exponential is crucial in some fashion. It's crucial because it's observable, because you can see it in your simulations and your experiments, or it's crucial because you need it to satisfy certain boundary conditions. The other thing about this picture that we have is that there may be lots of singularities in the complex plane. In fact, for nonlinear problems, there's infinitely many singularities, right? So usually the singularities will be a discrete set of points, an infinite number of, but countably infinite number of discrete points. But it turns out that because the exponentials are switched on, these exponentials have different magnitudes. And the size of the exponential is actually dictated by the real part of this chi. And it's usually the case that the further the singularity is from the domain of interest, the smaller the exponential. So usually you just care about the nearest one, is what I'm saying. So when you do this procedure, you're going to usually find the nearest singularity to the axis, and that's going to be the one that you're most interested in. But then there are lots of problems as well where you may need more singularities. And in theory, if you want perfect accuracy, if you want exponential asymptotics beyond, right, all the exponentials, you technically need to add all the singularities. But that's the general procedure. Now you can see that this general procedure is not reliant upon the fact that you have a simple differential equation. It can be a nonlinear differential equation, something quite complicated. The formula is always the same. You expand it into a series, you attempt to find singularities which lead to divergence because these are quite crucial. You attempt to characterize the late terms, and then you use the fact that the exponential is switched on this way. You'll also see that and again, something that I communicated earlier was that this universality is not subject to the fact that you're given a differential equation. So technically any divergent series that you've produced, either through a PDE or through a differential equation, is always going to have this. right? And again, just to stress, because obviously we're using asymptotic techniques in a huge range of fields, you don't always need to get exponentially small terms. It's only in a subclass of problems, but often very interesting problems, that these exponential asymptotics are crucial. Again, these are usually some of the most mysterious and challenging problems is to figure out these exponential asymptotics, but you don't always need them. They may be subdominant. They may be such that they never make it down to real space. And if your Stokes line is, it's going in that direction here and another one up there, you might switch on exponential here and switch it off. And by the time you get back to real space, they might be gone. Right? And that's the interesting bit. For me, for people in the sciences, you're all going to have a different differential equation. And then the interesting question is to draw the Stokes lines and to figure out what does that tell you about the actual solution. Okay, so we're going to leave it at that. We've covered now 3 of the classic examples of baby exponential asymptotics. We covered the exponential integral, the complementary Airy function, and then the Airy function. And then we covered in 3 ways deriving the same kind of techniques to deriving the exponential asymptotics, right? Eventually leading to this. And then I presented you these universalities. Now we're going to go into the interesting territory of, given some interesting nonlinear differential equations, and still linear, there's some interesting linear equations, let's apply these techniques without the use of integral transforms, without the use of steepest descents, and try to derive the exponential asymptotics. That's going to be the next set of interesting lectures going to the end of term. All right, thanks everyone. We'll see you next time.